talking about the basics of AI. In the second week, we introduced the tools that we usually use for AI applications. Now we're in week 3, and we will be focusing on kind of the first and possibly one of the simplest machine learning topics that people will encounter. That is linear models. And linear models, here we call it the models. Actually, we're talking about algorithms for generating models. And this concept is relevant to many concepts, many things that we do a lot in engineering, such as curve fitting, or in a linear case, we use linear regression or linear curve fitting. For the lecture and lab that we're going to do in this week, we have 3 objectives. First, after this lecture and the lab, you will need to be able to lay down the mathematical framework for the basic linear model. So we will start with the basic one, and then we will gradually add more fancier and more practical content to extend the functions of the basic linear model. And based on the mathematical framework, you will need to be able to develop your own code for implement the basic linear model. In this course, we have a few chapters that you will need to code the algorithm from the very beginning, and this is one of the topics that you will need to do that. And third, I put a star there. That means this one could be more difficult than the previous 2. And I think we will do that. That is, you will need to be able to explain the use of regularization and kernels in linear models. And these 2 things will give the linear models more functionalities. Regularization will help us to solve the overfitting issue, which is very common in machine learning tasks. And the kernels will give the linear models nonlinear capabilities. So you will possibly need to take notes in the first 2 lectures. Oh, sorry, I said I would share the slides. I'll do that. And starting from the week 3, we will be using notes for the lectures. First, let's take a look at overview. And you will also see that the way that we are doing the lecture here sometimes will be slightly different or even significantly different from what you could find in the textbook, in the reading materials. First, let's have an overview, and I want all of us to take a look at the data structure first. We did similar things when we are talking about the AI tools. For example, for NumPy, Pandas, they all have their own data structures. Actually, they share a lot of things in common. And also, when we are talking about the data in machine learning in general, I also offer some information about data structure. Here we got another one. It's the same thing, but it's a little bit more customized for machine learning, for linear models. And you can see that on the left upper corner, we have the data. The cells in green, they are unlabeled data, so they are X. And you can see that here, we use capital letter X, and we put a bar above it. That means it's a second order tensor or more complicated. When we say, hey, second order tensor, we mean when we have a 2D array. First order tensor, that's a vector. We will put a arrow on the top of it. So you can see for the xi, we'll put an arrow above it. That means it's a vector. That means a 1D array. So the capital letter X bar, that is the unlabeled data. Then for the Y, the object or the target here, we use one vector sign above it. That means it's a 1D array in this case, but it can have more than 1 dimensions. For example, in this case, I put a blank column here to say that it can be extended. But in this case, let's overlook it. It only has 1 column, and let's make it a 1D array. And also, we said when we are talking about models, we have parameters, ways to define models. Here, the parameters or the ways here, we have this W. You see W1, W2, W3, and we also have another thing called B. And if we take a closer look at the data, you will find that again, each row is one sample, one instance, and each column, that is one attribute or one feature of the data. So for each sample, you can see that there are like J, capital letter J attributes, and in this case, they're capital letter I samples. We use small letter I to represent the ith element, the ith sample in the data set. And we use small letter J, means the jth attribute in the set of attributes. But we use capital letter, means the total number. And for the capital letter X bar, the whole unlabeled data sets, so it is a 2D matrix. It has two subscripts, I and J. I means the number of data, J means the number of attributes. And if you take a look at the right for the weight, in this case, actually, we only have one column, but we could have more columns. But in this course, we only discuss the simplest case when we only have one column for the weight, for W. Because one is a column array, 1D array, so we have W vector, so it's a vector. Put a vector sign, an arrow above it. And usually if it's a vector, it's a column one, then it's just a vector. But if it is a row array, then we need to put this sign here. That means we transpose it, right? It turns into a row array. And what we're going to do, you will see that we will use these parameters, the weights. We use different ways to combine different attributes. So we will move from X to Y. As I said, for all the machine learning tasks or even engineering problems, what we're trying to do is just to find a mapping from X input to output Y, right? And for linear models, what we're trying to do is just to use a linear combination of different attribute values to create output Y. So that's the basic idea. And for linear combinations, that means it's a weight. You can also understand it as a weighted average, right? And the weights are here. So to get a weighted average, we just need to understand it this way. Originally a column vector or column array, then we transpose it. So we will get something like this. And you can see that the number of weights equals the number of attributes, right? So each attribute value has a weight. Then we multiply the attribute value and the corresponding weights. We get a lot of products. We add all the products up. We get the weighted sum. That weighted sum is the linear combinations of all the attribute values, right? That's how we do it.
Can you explain it with numbers or anything else, like the samples and attributes example?
For example, let's say that you want to talk about the class information, right? Then we will have 1, 2, 3, 4, for example, and let's say that each of us have an identifier, but we don't put it here. Let's say it's your name, but I put it here. Number 1 student, set. What is your weight? Attribute 1, what is your height? Attribute 2, what is your age? Attribute 3. Each of them has a number, right? And then for the label, let's say give everybody a grade, give everybody a score. That's not appropriate. Let's say that we're going to do it in that way. So that score, everybody has a score. That score is at the very beginning, we don't know the relationship of the score and different attributes. So we want to do a linear regression, use a linear model, right? Here what we're going to do is that we assume that the score is a linear combination of different attributes. For example, you have attribute 1, your height has a weight 0.5. This one 0.2, 0.3. You try to multiply the attribute value and the weight value, you will get a product, right? Then here you get a second product, you add all of them up, you will get one final value. Then we assume that the final value will be something like the score. So the goal of this thing is trying to see how to determine the weights so that this linear model can give us accurate predictions that are very close to the scores that are given by somebody else. We don't know the equations that they use for calculating the score, but we make assumption. We assume that we use linear model, so we assume there's a linear relationship between the object value and attribute values. Then we try to figure out weights. So the goal of the linear models is just to find out how to determine weights so that the linear model that we propose can help us move from here to here without knowing the exact equation. Then let's move back a little bit to review on the machine learning goal. Again, no matter you're talking about machine learning or any other traditional engineering applications, the goal is to find a mapping F. And so in a simple way, you can understand it as a mathematical function, but in many cases, we don't have basic mathematical equations for describing the mapping. It can be anything else. It can be a table, it can be a chart. So as long as you can move from one input to the output, then we call it the mapping. So we want to go from X to Y. And with this function, we know that what we're trying to do, we're trying to say Y equals X. That's what we're trying to do. That's the perfect condition. We find this mapping, and this mapping can help us get from X to Y. But here you can see that I try to make it as simple as possible. So X and Y, they have no vector signs above them, no tensor signs above them. But if we combine this simplest case and the data that we just observed in the above figure, and you can see that in this case, Y is a 1D column, so we don't consider this. It's 1D, then that means it's a vector. F is also a function of, but here, our X is 2D array, so it's a 2D vector, right? So we put a bar above it. That means it's a 2D array. And you can also see the concepts that we saw before, something we call X. X0, that's along the row direction, vertical direction. X1, that's the column direction or the attribute direction. So this is for the whole thing. But if we want to take a look at one sample, let's say for sample I, and we know that I is from sample 1 to sample capital letter I, then we will have yi. Now yi, that's the ith element in y, target vector. That will be a scalar, so there's nothing above it, equals fxi vector. Try to take notes if possible, because this is slightly different from what you can find in the textbook. B here is also scalar. That means it's only one number. As I said, here we are talking about linear models, right? In the first chapter, the way that we get the mapping is linear model. And the idea of linear model is the Y is a linear combination of the variables. Variables here means the attributes. So here you have J attributes that have J variables. They're just different things. Variables or random variables is a concept from statistics and probability theories. Again, variables and attributes, they're the same thing. They're just for different things. When we talk about sample data, we use attributes. When we are talking about data from a statistics perspective, we may use variables. And later on, when we are trying to plot the results, and you will see that, for example, if you only have x1, x2, and y, you want to plot the results, the data, you are going to have three axes. x1, x2, sorry, it's not xi1, xi2 for sample I, and then yi. So you're going to have a point with three coordinates, right, in a 3D space. If you only have one attribute, that means you only have xi, there's nothing else, not xi1, xi2, there's only xi, you have yi, then you want to plot the data, you will do it in a 2D space, right? You have x and y, then you have a point in a 2D space. So that's variables. You have two variables, you only have two attributes, you do it in a 3D space because you need to have one extra x for the target. If you only have a vector for the target. So with this linear combination of variables, then we can do the following things. yi equals, you can see that xi here. Actually, xi this is also a vector factor. But when we put it into the capital X array, then it becomes a vector 1. So because we transpose it, you can see that there's a sign here. We use this sign to turn it from a column array into a row array. But the original X is a column vector without the transpose sign. And for this one, it's a linear combination. An easy way to do the linear combination is something we talked about before. That's a dot product. So it's just xi vector transposed dot product, the vector of w plus b. If you want to take a look at what it looks like using matrix operations, we will have xi, the vector, originally is a column array. Now we use the transpose sign to turn it into a row array. So we're going to have xi1. This is for sample I. xi2, xij, something between, then all the way to xij, capital letter J. And this one, we also have the W1, W2, then WJ, finally W capital letter J. It's a dot product. So it's a column array times a row array times a column array. Then you get a product of the corresponding the first element of the row array and the first element of the column array. Then do the same thing for the second element in the row array and the column array. You get a product of all these corresponding elements, you add them up, that gives us a dot product, right? Don't forget a B here. So, but that's what we hope for. It's not going to happen because the function, you will find that the function that you propose, that you're trying to find to do that linear curve fitting, linear regression, cannot give us the perfect results. So this fx, the mapping, usually cannot be equal to the y perfectly. We can only approach it, but we cannot get to it. So we need to keep this in mind. That is, we use fxi to approach yi. To approach that, that means there's always a difference between them. And that would be error. Or in many cases, we call it a residual to be more accurate. And there are different ways to measure this difference, error or residual. And one common one is this. We use something called a Euclidean distance. So you get a difference between them, then you get the square of the distance. And that is also related to another concept called least squares. That's a very common method that we use in optimization. So we set up a cost function, then we want to minimize that cost function. Here, the minimized cost function is this one, so least squares. And if you want to get a better understanding, oh, what are you talking about Euclidean distance? And what is least squares? So here is one illustration. Let's say that we're trying to solve a linear regression problem with only one for data or with only one attribute. So we use X to represent that only one attribute, one, of course, the target. And for any data point, there's only one attribute value and only one target value. So get a 1 point. Then for the second data point, get a second one. You keep doing that, right? Then you do the linear regression or try to solve a regression problem, use the linear model. You will find that eventually we will find one curve. And which curve is better? In general, we want to find one curve, one straight line. It's linear, so it's going to be a straight line. That can pass through all the points, right? But however, that's just usually the best case. And we know that we have noises and data is not perfect. So then we will try to find a straight line, a curve, that is close to all the points. And how to measure the distance. Here we use the Euclidean distance. It's the distance that we use in 2D space. For example, we measure the distance from the points to the straight line. Then for each of them, the distance is actually just the square of the difference. Actually, square root of the difference. But here is the same thing. Some use the square root instead of this one. So some cases we use this one to measure the error. But here we use this one because it's simpler to use this one for both deriving the equations and for coding. And for every point, we can get a Euclidean distance. Then we add all the distances up. We get the total distance between the data points and the straight line, right? We want to minimize that distance. With this understanding, then we can lay down one general mathematical formulation for the regression task using a linear model. Then the regression. Again, regression means the target is continuous. The value, if it's discrete or not continuous, then we have a classification task instead. Using a linear model can be mathematically formulated as. So we use one equation or mathematical formulation to describe what we are trying to do when we're trying to address a regression task using a linear model. That is, we are trying to find the best model. Here, the best model is described by the parameters. Here we have two types of parameters. We have W and B. W is the weight and B is the offset. And you will see similar equations in the mathematical descriptions of machine learning tasks. So we are trying to find a model, and the model is described using W star and B star. Here the star signs means the optimum values. And what do we mean by optimum values? Next, we'll see that. We will see something like this, arc minimum. That means we are trying to find the parameters, the arguments that will help us minimize something following this. And the things that we're trying to change so that we can reach the minimum value, there are B. And the thing that we are trying to minimize, that is the loss function, right? Objective function. It is a summation. This summation goes from I equals 1 to I equals capital letter I. And it's a summation of the squares, the Euclidean distances, xi vector minus yi. And to write it as the linear model form, because now this is the general form for all the regression tasks using the least squares. Here we wanted to write it for linear model tasks. So we still have the same thing. We try to find the parameters that would help us minimize the following functions, and the parameters that we are trying to adjust so that we can minimize this loss function, they are W and B. So we write out this F function here, how to do the mapping in a linear model. We use a linear combination of different attributes. This is dot product because we have two vectors here. This is the description of it. Make sure you can do it. For example, somebody said that how to mathematically describe regression test using linear model. Then you should be able to write down this. We're trying to find the optimal W and B value that will help us minimize this loss function. That's the meaning of it. So how to minimize this function? That's something that we will discuss later. There are different ways. One typical way, of course, you can use some optimization method, right? You have something, they will do it iteratively and help you to reach the minimum value. That's one way. But in today, we're going to do it in a different way. In a few cases, we can find analytical solution to the problem. For example, for this problem, we can find an analytical solution. So we don't need to use the optimization thing. Later, for complicated machine learning techniques, for example, deep learning, even the shallow neural network, you will find that, we will need to use optimization. There's no analytical solution. All right, next, let's lay down the general formulation of basic linear model.
This is going to be 3.
We have this one overview, so we have two subheadings. Now we jump to the second major heading. The different linear model algorithms. We're talking about the basic linear model algorithm, and later on we will show how to get more complicated linear model algorithms based on the basic one. Again, now we are trying to formulate the equation. Use this. We're trying to get a function to get from all the data, not just one sample anymore. So we try to get a function of x. That one will be x bar, the dot product between x bar and w plus b. And we try to use this one to approach y vector y. To give you guys a better idea what we are talking about here, let's write down the array formulation of this equation. So here you can see that I'm slowing down intentionally to let you guys get familiar with different formulations. They're the same thing. So after you're familiar with these things, when I write it in one way, you should be able to automatically recall the other ways. X, capital letter X, X11, X12, X1J. So this is sample 1 corresponding to column 1 in the data set. X21, X22. Again, this I thing, the first subscript, this I, that's the sample number. That's also the column number. And the second subscript, this one is the attribute number. So the last row will be the last sample. We use the capital letter I. It's a dot product. And you're going to have the W vector, W1, W2 to WJ. And we know that when we have the dot product, the first row of X will be multiplied with the W vector. So they should have the same number of elements, that is J. So here, let's say that it has I by J or I times J elements, and here has J times 1. And we know that when we have dot product, that means we have one contraction. When there's one contraction, the two axes that will be contracted will have the same number of elements. So I by J times J by 1. The two arrays will give us a new array that has a dimension of I, the shape I by 1. Here we still have a B here. B is a constant, so it does not matter. It will be added to every element. Here we get a Y, Y1, Y2. Again, Y, we know Y, there are I samples. So Y should also have their Y target values. And you can see that this column array has a shape of I by 1, right? You can see that this I by 1 and this 2 will also give us I by 1. So they're consistent. But usually we don't do it this way. We want to make one more change. That is, you can see that there's a B here, right? The B is different from all the other things. There's only one number. So what do we usually do? We treat B as part of the general coefficient. That is, we try to combine W and B. We generate a new thing for the general coefficient. That's W hat. W hat is also a column array. With hats, we will get a new formulation. Here now, the mapping is a function of X hat, not X. You will see that it would be different from the original X bar. Fx hat equals the X hat, then dot product between X hat and W hat. This is actually a very common operation when we are playing with arrays or matrices. How to do it is very simple. So everything here would be the same, still IJ, but there's going to be one thing, add 1 here. And W1, W2, all the way to WJ, and B now becomes the last element of this W vector, W hat. And if you don't understand why we do it this way, then just compare this formulation and what we have above. They're the same thing. So Fx equals, you can do that, equals X11 times 1 plus X12 times W2 plus all the way to X1J times WJ, then plus B. Here you can see that if you do it, it will give you exactly the same thing because everything here will be the same. And then finally you plus 1 times B. We do it and you will find that later when we are showing the solution, the deductions, that will make things look much simpler. Again, let's take a look at the number or the shape of arrays. The shape of arrays will be a significant thing when you want to do the coding yourself. You will find that will be significant. In some cases, when you are supposed to use a column array, use a row array, you will get a message saying that, oh, you got, they cannot be multiplied. So for this one, we still have I rows, but now we have J plus 1 columns. We have J plus 1 rows and 1 column. So the product of these two things will give us an array with the shape of I by 1. So that's the same thing. That's what we want for I. We'll get the same I. That will make no difference. I still be I by 1. All right, with this general formulation, next, let's come back and talk about that loss function. So the loss function using the least squares method is, we usually use this L to represent the loss function. Loss function is a function of the general coefficient W hat. So when we have different W hats, we can have different loss values. We use the Euclidean distance. Actually, here is the square of it. That's fx hat, capital letter X, minus y. Now it is a vector. So we are following what we did here. It's a square of distance. And then we write it using the arrays. We will have x hat, then we have dot product W hat minus 1 vector y. And we need to transpose this. Then get the dot product of this one and x hat W hat minus vector y. So we know the loss function. Now we can write the math formulation of the regression problem using the basic linear model is this. So we are trying to find the optimum weight. We still have the same operator. Actually, in detail, we're trying to play with both W and B, although we have combined them into general coefficient vector W hat. And the loss function that we are trying to minimize is what we just wrote down above. And if we write this out in detail, we would have this. So that is mathematical formulation. Again, the cool part about this is that this problem have a closed form solution. The above regression problem has a closed form solution. Here, I will not get into the detailed deduction. You can find it. And for us, we just need to know that there's a closed form solution, and we also need to develop some code to implement it to solve a real linear regression problem. The solution is this. It has a shape of, again, J plus 1 rows, 1 column. This one can be obtained using the following products. That is x hat. I write down the shape of every array to facilitate your later coding process. Here, this is the shape of x hat transposed, not the original x hat. So original x hat has the shape of I by J plus 1. Then we want to get inverse of the dot product between these two arrays. Then we have another dot product here. So always pay attention to the shape of different arrays. They matter a lot in your coding process. There are two significant things in linear models. They do not only apply to linear models, but also to some other things. So that's why I want to bring them up. So these two things, the first one is called regularization. Regularization is needed because it's a very useful tool that we can deal with overfitting, because overfitting is one major issue that we can encounter in machine learning. And you will also see regulation in some later lectures for some other machine learning algorithms. That's the first thing. And if we add regularization in that basic linear model, we will obtain of some other common linear models, such as ridge, lasso, and the elastic net. I will show how to add linear regularization to linear model to obtain these three models. The second thing that we also need to know about is something called about the extension of regression models to classification models. If you take a look at the machine learning algorithms, you will find that Some algorithms, they're by nature for regression, such as linear models, right? You can see that you can get a curve, deal with numbers. And some models, like what we will learn in the following lecture, that is the decision tree, you'll find that that's by nature is good for classification, not for regression. So for a linear model which was proposed for regression by nature, we need to find out a way to extend such models so that it can be used for classification. And a common way of doing that is we add a few more things to it. For example, we add something called a logistic function or a softmax function to the model so that we can extend the model for classification. For classification, we have two types. One is called binary classification, when we only have two categories. The other one is called multi-class classification, when we have more than two categories or classes. And a logistic function and a softmax function are good for these two types of classification tasks, respectively. We will introduce them one by one. Let's first take a look at linear models with regularization. Again, the lectures that we are having today may be a little bit boring, so please bear with me. And they do not just apply to linear models. You will see them in later lectures as well. First, as I said, regularization is an effective way of addressing overfitting. If you do some machine learning work, and you will find that overfitting is really one of the most serious issues that you can get in machine learning applications. And if you want to take a look what overfitting looks like, we explained this in the previous lecture. So here, let me use one plot to show it again. Let's see that we want to do a very simple linear regression. We have 5 measurements. One way to do it, of course, for example, we propose a model. Let's say in this case, it's not linear anymore. We can get a fitting curve, a function, or a mapping like this, right? This is one way of doing it. Some people say that, oh, I'm not very satisfied with these regression results. I want to do a little bit more. So I use a more complicated fitting function for it. And in the first try, you can see that the results are not perfect because the curve does not cross all the measurements, the points perfectly, the distance between them. And if we use a more complicated model, we will see we can get something. For example, we use a model like this. For a model like this, you may say, oh, this one seems to be better, right? At least we are talking about the accuracy of the loss. This curve is closer to the measurements. But now the question is it better? So we use second curve. We can see that obviously this model, the second model, is more complex. If we don't understand it, the easy way is that if we're using a polynomial, we will see that this polynomial will be more complicated, high orders, so it will have more coefficients or more model parameters. It does not mean that the lower loss or the higher accuracy you would get, the better the model would be. With something like this, what happens is that we know that for the measurements, there are always errors, there's always noise in it. We use an overcomplicated model. What's going to happen is that a model will learn case-specific patterns or features, the noise, learn errors as well. And those patterns about the noise, the errors, they cannot be applied to other data sets. So they only work well for this data, this case, but when you apply it to something else, it does not. So in this case, we want to add something to address this overfitting. Make sure that our model is not overcomplicated. And a typical way of doing that is regularization. And the idea of this regularization is that it includes the number, total number, and the values of model parameters in the loss function. We know that in order to solve the problem, you either use an analytical solution or use some optimization techniques, and the purpose is to minimize the loss. So if the number or the values of the model parameters is part of the loss function, then when we are minimizing the loss function, we will make sure that we don't have that many model parameters in the loss function. In that way, we can control the complexity of the model while we are minimizing other terms in the loss function. So in this way, we can deal with two things. One, of course, is the model accuracy. So that's one major purpose. We want to get a solution. We want to make sure that we can get a model that's as accurate as possible. And we can do it using the basic linear model. But now we add more thing, add a regularization. So with that, now the loss function you can also consider model complexity. And to give you guys a general background, that is, we have something, that's a general rule, something called Occam's razor's principle. And this is a general principle, not just for machine learning. So this Occam's razor's principle says that when we have different things, different models, for example, machine learning models, and they have the same accuracy or same or comparable performance, in that case, simpler models are better. So that is when we have things with comparable performance, let's always choose the simpler ones. So that is all the Occam's razor's principle. And getting back to this, we use this rule as well. So we are trying to get something that's both accurate and simple. And when we are considering these two things, accuracy and complexity, of course, we will need to use some ways to emphasize which one we more care about. And you will see that in the following equation for the loss function with regularization terms. By adding regularization to the loss function, we can get more complicated linear models. The first one is the ridge model. The ridge model or ridge regression is a linear model with L2 norm regularization. L2 norm or vector, there are different vector norms, L1 norm, L2 norm. They're just different ways to get the magnitudes of the vectors, the different ways of measuring the magnitudes, similar to the concept of the distance. In the previous vector, we talked about the Euclidean distance. Let me give out the equation for the loss function in ridge. So it's constructed using the model parameters as well. It's very similar to the one that we used before. So this is what we had before, the first term. Now we add one more term to the right of it. And if you want to ask what L2 norm looks like, it's the L2 norm of the weight vector. So it's just a vector or inner product between the generalized weight vector and it itself. And you will also find a new thing here. Lambda is a weight that we use to adjust the significance of the regularization term. If we increase that value, then we care more about the complexity. We reduce it, we care more about the accuracy. And this regularization term, if you want to see what it looks like using specific weights, we can reformulate it a little bit. In the previous lecture, we said the number of weights is identical to the number of attributes. So we also have J here. Actually, here should be J plus 1 if we take into consideration that B as a term of this generalized weight vector. And with this loss function, the ridge regression problem can be formulated as. So we are looking for the optimum model with model parameters. W hat star, star means the optimal one. And this one will be obtained by minimizing the loss function, which is parameterized by the model parameters. Fortunately, we also have a closed form solution to this problem. So we don't need to use optimization. We can just implement the closed form solution to get the model or the model weight parameters. And the solution has a format that is close to the closed form solution that we got for the basic linear model. There's one difference here, that you can see a new term here. That is this I thing. We put a bar on top of it. That means it's a second order tensor. In this case, if you take a look at the dimensions of the other arrays, you will find that this one will have a shape j plus 1 by j plus 1. And if you wonder what a identity or a unit matrix look at like this, it has ones on the diagonal, and for all the elements of the diagonal, there would be 0. So that is the identity or unit matrix. So you can see that you should also be able to implement this rich model just by adding this new thing. Of course, you also need to determine a number. If you don't know how to do that, just set a number there and try to see what you will get. And every problem will be different. First, that's rich model. Second is another popular linear model called lasso. The difference between rich and lasso is that lasso using a L1 norm regularization. So you use another way to measure the magnitude of the weight vector W hat. So let me write down the loss function so you can compare these two methods. And everything will be different until the regularization term. So you can see that here we have squared. We use the sum of all the squares. But here is the sum of the absolute value. That's L1 norm. Just a different way of measuring the magnitude of the vectors. And with this one, we can formulate this problem, the lasso regression problem, in a very similar way. So I'm just copying everything. And for this one, there's no closed form solution, unfortunately. And the reason is that this loss function is not differentiable. That means you want to get the derivatives, you'll find that you cannot get the derivative values at some points because it's not differentiable. So a closed form solution is not available except for very special cases. For example, when we have something called orthogonal normal strip matrix. So we don't talk about that. If you still want to solve the problem, now there's no closed form solution. The way to do it is to use optimization. And in Python, that's not difficult to do because there are many packages in Python that you can use to solve optimization problems, as long as you specify what optimization method that you want to use. What we need is just to give out the loss function and the parameters that we want to optimize. We give out those two things as the arguments for the optimization function, then we click run, it will give us the answer. The answer is, of course, the optimum parameters. That's for lasso. There's another one. If you check scikit-learn, you will find another linear model. It's called elastic net. Elastic net is just a combination of rich and lasso. If you know how to do rich and lasso, then you would know how. You should be able to know how to deal with elastic net. That is one topic we want to cover. That is regularization. In later lectures, for example, for artificial neural networks, we will also try to add regularization to the loss function in a similar way so that we can consider both the accuracy and complexity of the model. This is very significant in topics such as deep learning, because in deep learning it's very easy to add more layers to an artificial neural network to make a model super complicated. And because of that, it's quite easy to get overfitting issues. And to do that, one way to do it is to adding the regularization. But of course, there's some other techniques that we can deal with regularization and the overfitting, and regularization is one of the simplest one. Let's move to the second topic. That is how to extend linear models for classification. And you should have seen things such as logistic regression. So by adding new functions like a logistic function, softmax, we can now use regression models to do classification. So in a simple way, we can include all of these things into the logistic regression. Again, the purpose is to extend linear models to classification tasks. First, let's take a look at binary classification when we only have two classes or categories. And we know that when we are doing regression tasks, the label, the target are continuous numbers, right? And when we are doing classification, they're not continuous anymore. They're discrete numbers or some other symbols. So an intuitive thought of converting a model that is proposed for regression to classification is to find a way to map the continuous output to a discontinuous output. And one way of doing that is to introduce some extra functions such as logistic and softmax that we will be introducing today. So again, we're trying to do is for regression, we know that usually we get continuous output. Such output, it can be anything from negative to infinity, so it can be pretty large. And in order to convert this one into the discrete things, usually we do it by two steps. In order to convert this one to classification and with discrete, we'll do first, we squeeze the output into a small range. Second, we set a threshold in that range. Above it belongs to one category, below it another category. That's for binary classification. And for multi-class classification, we want to compare possibilities of one sample belonging to different categories and choose the category with the highest possibility as the true label. Second one, threshold, or use the maximum probability. For squids function, for binary classification, we use a logistic function. It looks like this. Let's say that z is a function of y. We write it in this way because we know that in the original model for regression, the output is y. So here we want to convert y to a new thing, z. The function itself is not too complicated. You can either write it as this way, 1 divided by the sum of 1 and e to the power of minus 1. Is equivalent to e, the exponential 1 divided by quantity 1 times e to the power of y. And if you want, take a look what this equation looks like. I can draw it here. It's like this. So now the horizontal coordinate is y, and the function value or the y coordinate, that's z. The z value ranges from 0 to 1. So the middle of it is 0.5. And for this function, y can be anything from negative infinity to positive infinity. However, when y approximates the positive infinity, z will approach 1. If it goes along the other direction, the negative infinity, then z will approach 0. The middle point is the value of z equals 0.5. So you can see that now we successfully squeeze the function y into a small range for z from 0 to 1. With this, we can do the second step, use a threshold, for example, 0.5. Above it, we said that if we do the calculation, we get a y, we use this function, get a z, the corresponding z value. If it's above 0.5, we say that it belongs to category 1. If it's less than that, we say that it belongs to category 2. So in this way, we can use a model that was originally developed for regression to the classification tasks. Let's take a look at this logistic function to get a more in-depth understanding of it. If we reformulate the logistic function, you will see another thing. That is, you can do it yourself. So here, I will not show how to do that. That is e, that's the natural number e to the power of y equals z divided by 1 minus z. This is very interesting because we said that if z is the probability that the sample with an output y belonging to one category, then 1 minus z, because z ranges from 0 to 1, should be possibility that sample belonging to the other category in a binary classification problem. So that means e to the power of y. That's the ratio of possibilities of this sample belonging to two different categories. If we look at a specific sample I, we can write the equation in this way. It's the same thing, but we just make it a little bit more specific. So again, Zi, that is the possibility of sample I belonging to one category. Here, let's say it's category 1. So when you are coding, you specify how you're going to name it, category 1, category 2, or category 0, category 1. Let's here call it category 1. And for this one, the possibility of the sample belonging to it is P. Here we use the hat here. Hat means define the label in classification, not the label in regression anymore. For this sample I, when it belongs to 1, when equals 1, and here we put this sign here, means the model has the parameters x, w, and this is Zi. We can also put an I here. That means that's for sample I. You will get rid of the I, that's for any sample. 1 minus Z, because if the possibility of the sample belonging to one category is Zi, then the possibility that it belongs to the other category is 1 minus Zi, because Zi only has a range from 0 to 1. For example, if the possibility that I belong to category 1 is 0.8, and there are only 2 categories, that also means that my possibility belonging to the other category should be 0.2. Possibility of sample I belonging to the other category. Now let's call it category 0, and we can write down a similar equation. Here, P0 or 0I, we are talking about a sample I, yi equals 0. Again, it has a hat on it. That means it's a label for classification. So it can be only 0 or 1. And again, I in this case is just the ratio of the possibilities belonging to the 2 categories. And in this example, actually we made one hypothesis for relating the labels between labels for classification and the labels for regression. For classification, yi hat or y hat I equals 1 if P1 is greater than or equal to 0.5. That means we select the threshold of 0.5. It is worthwhile to mention that we can use other threshold values, but 0.5 is the most common one for binary classification. And with this keep in mind, next thing that we can do is how to construct a loss function. For this one, binary classification, we use something called a cross entropy. If you take a look at the reading materials, the book chapter 1, you will find something for it. Cross entropy function, that's something from the information theory. So this function is usually used to compare 2 different things. For example, 2 things with different distributions. And because of that, we can use it to compare the true labels and the predictions. The way of doing that is just use a function like this. In a simple way, let's say that we have 2 things, y1 and y2. One is the true label, the other one is the prediction. Then the product of y1 and the natural log of y2, that will give us the cross entropy. It's the combination of 2 things. And we use this one to measure the difference between y1 and y2. And for a classification test, we know that we want to make sure the predicted labels are close to the true labels. So we want to make sure that the difference is as small as possible. So then you use this cross entropy for the loss function. We minimize this cross entropy between the true label and predicted labels. Then we will minimize the difference between the true labels and predicted labels. That is the error, right? And with this, let's move to the next page. All right, let me give out the function here, loss function. So for every sample, we will get a cross entropy, then we add them up for the whole data set. That's why we have a summation here. We'll go from the first sample to the final one. That's the capital letter I. Here, because we have 2 different classes, categories, so we want to consider both of them. And if you take a look, you will find that the first, for each product, The first is the actual label, and the second one, that's the prediction. But the second term, that's the same thing. That's the actual, and here, the prediction. And the first one, that is category 1. And here's for category or class 2. Then the formulation of the logistic regression problem. That's for binary classification, is this. It's similar to the formulations that we give out for other linear model problems. We try to minimize loss functions so we can get the optimum weights, W and B, or W hat, by minimizing this loss function. That is for binary classification. Next, let's take a look. Multi-class classification. So compared with binary classification, it's similar in many aspects. For binary, what we just did is that we just used the logistic function. But for multi-class, when we have more than 2 categories or classes, we use softmax function instead. The softmax function is similar to the multi-class, to the logistic function, but now since we have more classes, we will do it in this way. It looks like this. This is also a function that we use to convert the output of the regression problem, which is a continuous number, to a probability. So that's for squeezing. Let's say that we have sample I. We want to get its possibility of this sample belonging to category K, small letter k. P means probability. This one can also be written as P, Y, I, K, belonging to this category, so we'll put a hat on it. And the real equation is this. E to the power of yik. That is for sample I, the possibility that, yik is the output for sample I. But for the output of sample Y, it will have capital letter K output for the capital letter K categories. The denominator is just the sum of all this E to the power of yik. Again, this pik is the probability of sample I belonging to category K, small letter k. And small letter k belongs to a set from first the category to the last one. That's the capital letter K. So getting back to a typical problem, we have for any sample, let's consider this case. For input, we have sample I, and we feed this sample I into the model. We will get the output. If we don't do anything to it, it's for regression, right? Then the output will be something like this. We'll do it in this way. You will get, depending on how many categories we have. For example, now we have 5 categories. We would get an output with 5 numbers: 0.1, 0.2, 0.15, 0.55, last one, 0.1. The total of them will be 1. So that's a possibility of this sample I belonging to different categories. And if you take a look here on the right, you have category 1, 2, 3, 4, 5. And if you take a look, you will see that, now the possibility that this sample belonging to category 4 has the highest value. So we say that it belongs to category 4. So in this way, we can convert this Y. So I missed one thing. Our original output is a continuous number. We need to use softmax here so that we can squeeze it into a range of possibilities between 0 and 1. We add softmax here. This is the original model. We add something here, softmax, just like what we did in binary classification by adding the logistic function. We squeeze the values into 0 and 1. Then second step, we select, instead of using a threshold, we just select the highest possibilities as the predicted label. So what we did here is select the category with the greatest probability as the predicted label. And the way of doing things like this will create another thing that's very popular. So this will lead to the wide use of something called one-hot labeling. That's one way of label our data. Actually, we already got in contact with it in binary classification, but we did not call it in that way. So this one-hot labeling is something like this. Because we know that for a multi-class classification problem, we want to see which category this sample belongs to. So one way of doing that is that if we have 5 categories, in the above example, only the 4th element corresponding to the 4th category equals 1, and all the other ones equals 0. 1 means true, the other one means false, 0 means false. So that is one-hot labeling. For example, one way of doing the labeling is that for every sample, you give it a number. 1, if it belongs to category 1, 1. If it belongs to category 3, you put a 3. That's one way of doing the labeling for classification. Another way is that instead of just using one number for one sample, we use an array. For array, the number of elements equals the number of categories, and only one element has a value of 1, and that marks the category this sample belongs to. The reason that we want to use this is this can be used in the later loss function construction. So with the one-hot labels, a loss function can be constructed as. It is also similar to the loss function that we got for binary classification. It's also a summation of something that's like cross entropy. It's a summation for the cross entropy values for different samples. From first one sample 1 to the last sample, capital I. It's a cross entropy, so we have a minus sign here. Then we have a product of things from 2 different distributions. Here one is for the actual, the other one is for the predictions. For the actual one is a label for sample I belonging to category K times the prediction, PIK. That's what we predicted using the softmax function. You get the original one, use softmax function, you can squeeze it into possibilities. That's PIK. So again, the first one, this is the actual, and we use one-hot labeling. The other one, that's the prediction. Then we write out the equation for P. It's just the softmax function. Again, this YIK thing, that's the predicted output of the original regression problem. And we use the softmax, we converted it to the output for the possibility. And for the training process, we just need to minimize this equation so we can get the optimal model parameters W hat, just to minimize loss. I will not write down that formulation again. It's very similar to what we did before. Here I just want to see for testing is a little bit different. So for testing, what we need to do, just putting the sample for any sample, let's call it sample I. Just put it in and let it go through the model. We will get the YIK, and then we convert it to PIK, and then we check all the PIKs. This is just this, everything, and then find the maximum value, and that the category corresponding to that value will be the category this sample belongs to. That's how we do it in a testing process. And these are what we need to know about for extending a regression model to a classification task.
I think I'm falling for you.